Hi, hello dear students. Welcome to physics class of PU2. We have been discussing about the chapter atoms. In the previous video class, we have discussed and we have derived two important derivations. One is the radius of the nth stationary orbit, and another one is what the total energy of the electron in the nth orbit. The expression for the radius of nth stationary orbit is by applying to a hydrogen atom Z is equal to 1 n square h square epsilon naught divided by pi m e square, and the total energy of the electron in the nth orbit is minus m e raised to 4 z square divided by 8 epsilon naught square n square h square. So by putting z is equal to 1, we can apply it to for what? Hydrogen atom, right? So here the total energy of the electron in the nth stationary orbit is negative, right? Which indicates what here? The electrons are bound to the nucleus, and the electrons are not free to leave the atom. That the negative sign indicates here. So now, from this equation, that energy of the electron in the nth stationary orbit minus z square m e raised to 4 8 epsilon naught square n square h square. Now we are going to express this in terms of electron volt, and we are going to apply it to for hydrogen atom. So where in this expression the m is the mass of the electron, e charge of the electron, epsilon naught permittivity of free space, h is Planck's constant, and their corresponding constant values are given here. The mass of the electron is 9.1 into 10 to the power minus 31 kg, and the charge of the electron, its magnitude is 1.6 into 10 to the power minus 19 coulomb, and epsilon naught value is 8.854 into 10 to the power minus 12 farad per meter, and the Planck's constant is 6.626 into 10 to the power minus 34 joule into second. So now with all these constant values for hydrogen atom, we are applying it to hydrogen atom. Its atomic number is Z is equal to 1. So hence the energy expression becomes minus m e raised to 4 8 epsilon naught square n square h square. Now let us substitute here all the constant values in this equation. Now let us put all these values in this constant values in this equation, so that we get, by substituting all these values and solving, we get the value as minus 2.18 into 10 to the power minus 18 joule, right? Minus 2.18 into 10 to the power minus 18 divided by n square joule. This value we are getting here. By substituting and solving, we get here. Now where n is the principal quantum number, and here the energy expressed in joule. So in this expression the energy is expressed in joule, right? Minus 2.18 into 10 to the power minus 18 divided by n square joule. Now where n is the principal quantum number, now I am going to convert it in what? The electron volt. So atomic energies are expressed in electron volt here. What is electron volt? It is another unit of energy used in atomic and nuclear physics. What is an electron volt? What is an electron volt? It is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. That is called as the 1 electron volt, and the energy gained is equal to what? 1.6 into 10 to the power minus 19 joule. So 1 electron volt in terms of joule is equal to what? 1.6 into 10 to the power minus 19 joule. So to convert this joule to electron volt, now divide the above equation by 1.6 into 10 to the power minus 19. So after dividing 2.18 into 10 to the power minus 19 by 1.6 into 10 to the power minus 19, you get minus 13.6 divided by n square, where n is the principal quantum number. So now we are at the stage of what? The expressing the energy of the electron in the nth stationary orbit in terms of electron volt, and only we have the constant term is here the principal quantum number n. So where n takes values 1, 2, 3 and so on, right? So now we have got the equation here, right? The energy of the electron in the nth stationary orbit in terms of electron volt with only one constant term, that is the principal quantum number n, right? So En is equal to what? Minus 13.6 divided by n square. Now the next point here, now we are going to study here about the energy level diagram of the hydrogen atom, right? So in order to draw the energy level diagram of an hydrogen atom, so we must know the total energy of the electron in different stationary orbits, right? So now we are going to study here the energy level diagram of an atom, that is we are going to apply it to hydrogen atom. So that to draw the energy level diagram of the hydrogen atom, we must know what here the total energy of the electron in different stationary orbit, that is n is equal to 1, n is equal to 2, n is equal to 3 and so on. Now we have already got here the total energy of the electron in the nth orbit of the hydrogen atom, that is minus 13.6 divided by n square electron volt. So by substituting the values n is equal to 1, 2, 3 and so on, we can find the total energy of the electron in various stationary orbits of the hydrogen atom. So now let us calculate here what the total energy of the electron in different stationary orbits of hydrogen atom, right? So now you can refer this table and also the energy level diagram. So now see here, so I have given here the table, orbit and the energy. So minus 13.6 divided by n square electron volt. So if you put the n is equal to 1 in this equation, so the energy of the electron in the first orbit is equal to what? The minus 13.6 electron volt, right? So the energy of the electron in the first orbit of the hydrogen atom is equal to what? Minus 13.6 electron volt, the first one. And if the orbit is equal to 2, that is the principal quantum number is equal to 2, n is equal to 2, so just put n is equal to 2 here in this equation. So minus 13.6 divided by n square, so 2 square is 4, so minus 13.6 divided by 4 is equal to what we are getting here? Minus 3.4 electron volt, right? So second one, so the energy of the electron in the second orbit n is equal to 2 is minus 3.4 electron volt. And again and so on, what we can write here for n is equal to 3, n is equal to 3, what we can write here? 3 square, so minus 13.6 divided by 3 square is 9, so minus 13.6 divided by 9, so it's the value we are getting here is minus 1.51 electron volt. And fourth one, n is equal to 4, if you put then minus 13.6 divided by 4 square, 4 square is 16, so minus 13.6 divided by 16 is equal to what? Minus 0.85 electron volt, right? So in this way, now what we have done here, the calculation of the energy of the electron in the various or different stationary orbits we have got here, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4 and so on. In this way, by using the formula you can calculate here, right? So now I have shown here in the figure the energy level diagram of hydrogen atom. The total energy of the electron in stationary orbits are represented by what here? The horizontal line with suitable scale we have used here. So this diagram represents what here? The total energy of the electron in stationary orbit is represented by what? The horizontal lines we have drawn here, right? The horizontal lines are drawn here, right? N is equal to 1, n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5 and so on. So now you can see here, as you can note here, the total energy of the electron is increases. That means what? It becomes less and less negative. So it becomes less negative. What it indicates here? The energy of the electron goes on increases, right, as you go to the higher orbits. And finally at one stage it becomes what? The energy is equal to 0 and the electron becomes free. So at infinite state, what happens? That En is equal to 0 and the electron becomes free, right? The electron becomes free. So now let us discuss here the some important points related to this energy level diagram, right? The first point related to this energy level diagram is the hydrogen atom has only one electron. You know this. Hydrogen atom has only one electron and it normally occupies the lowest level. That is the and the energy of this level is equal to what? The minus 13.6 electron volt. Because it has having the only one electron, it occupies the n is equal to 1 level. And when the electron is in this level, that is the atom is said to be in the ground state, right? When the electron of the hydrogen atom is in the n is equal to 1 state, then we say that the electron is in the ground state, or the atom is said to be in the ground state. And at room temperatures, nearly all the atoms of the hydrogen are in the ground state. So this is the first point of this energy level diagram, that is the when the electron is in the n is equal to 1 state, the atom is in the ground state. And if the hydrogen atom absorbs the energy, the electron gets promoted to what? One of the higher energy level, then we say that the atom is in the excited state. Suppose if the atom absorbs the energy, right, due to rise in temperature or other things, the electron gets promoted into the what? The higher energy level. That means what? The electron jumps from, suppose if it takes the energy is equal to what? The difference between the energies of n is equal to 1 and n is equal to 2 levels, then that electron jumps to what? The n is equal to 2 states. If it takes the energy, that is what? The difference between the energies of the n is equal to 3 and n is equal to 1, then that electron goes to what? The n is equal to 3 state, right? Now we say that the atom is in the excited state. So when an electron is promoted to higher energy orbits, higher energy levels, it takes the energy due to the rise in temperature or other things, then it goes to what? Higher energy state. Now we say that the atom is in the what? An excited state, right? Thus what happens here, when the electron occupies the other than the lowest energy level, then we say that the atom is in the what? The excited state. So it should take the energy, it absorbs the energy to go to what? Higher energy orbits from the ground state, right? And the hydrogen atom, the excited state of an atom is a very short period. So after about 10 to the power minus 8 second, that electrons remain in the excited state, or atom is in the excited state. Now in this in the time interval of this electron, that falls back into the what? The inner orbit, right? So again what happens here, when an electron goes to a higher orbit by taking the energy, after a short interval of time of 10 to the power minus 8 second, that electron falls back into the what? The lowest state or the ground state, right? And during this state, what happens? The electrons or the atom releases the energy in the form of electromagnetic radiation. So whatever that atom or the electron taken the energy initially, that energy is emitted in the form of electromagnetic wave or electromagnetic radiations, right? So when initially n is equal to 1 state, for example, then it goes to what? N is equal to 3 state by absorbing the energy. After a short interval of time, what happens? It returns to what? Ground state. It returns to what? Ground state. So during that time, what happens? This the absorbed energy is emitted in the form of electromagnetic radiations, right? So it is emitted in the form of electromagnetic radiation. So this is the second point we are discussing about what? The excited state, right? And the next point is what? The total energy of the electron as the value of n goes on increases, right? As the value of n goes on increases, at n is equal to infinity, right? We have n is equal to 1 2 3 and so on. At n is equal to infinity, if the electron is raised to n is equal to infinity level, that means what? It becomes free, right? It becomes free. Now we are going to define here the two important definitions, that is what? The ionization and excitation energy, right? Ionization energy and excitation energy. So what is we have said here? Excited state. The excitation means what? It is a process of taking an electron from its orbit to the higher orbit, as we have discussed now. It goes from the ground state to what? Higher orbits, right? The minimum energy required to raise the atom from its ground state to excited state, it is called as what? The excitation energy, right? So if an electron goes from n is equal to 1 to n is equal to 3 state by taking some energy, right, that energy is called as what? The excitation energy. The minimum amount of energy required to raise an electron from the ground state to what? Higher energy state, right? That is called as excitation energy. Now what is an ionization energy? Right, what is an ionization energy? The amount of energy required to remove an electron from the ground state of an atom to what? Infinite distance from the nucleus, and that is called as what? The ionization energy. That means what? The atoms becomes free here, or the electron becomes free here. So the electron becomes free here. So what happens? The energy required to remove an electron from the ground state of an atom to infinite distance from the nucleus, that is called as what? The ionization energy. The minimum energy required to, what we can call here, free the electron from the ground state of an atom. What we can call here, the minimum energy required to free the electron from the ground state of an atom to, from the ground state of an atom, that is called as what? The ionization energy. So these are the two important definitions here. One is the ionization energy and another one is excitation energy. Excitation energy is what? The amount of energy required to raise the electron from the ground state to higher energy states, and ionization is what? The minimum amount of energy required to free the electron from the ground state of an atom, that is called as ionization energy. The ionization energy of an hydrogen atom is 13.6 electron volt. So we have the minus 13.6 electron volt. The energy is having the hydrogen atom or the electron in the first state of an electron. So we have to give the energy of plus 13.6 electron volt to remove the electron from the hydrogen atom, and then it becomes free. That is plus 13.6 is the ionization energy of the hydrogen atom. So this is about what? The energy level diagram. So this is about what? The energy level diagram of the hydrogen atom, and this is very important to discuss about the what? The spectral series of hydrogen atom, right? To discuss the spectral series of hydrogen atom, this energy level diagram is very important. So what is the energy of the electron in the n is equal to 1 state? What is the energy of the electron in the n is equal to 2 state, 3 state, 4, 5 and so on? Right, this is the energy level diagram of hydrogen atom. We have represented here, and we have discussed what is meant by excitation energy, and what is ionization energy, and what is ground state, and what is excited state, right? And when the atom is in the excited state, after a short interval of time, it comes to the ground state by emitting the energy in the form of electromagnetic radiations. Now with all these discussions, to discuss about the what? The spectral series of hydrogen atom, we need to discuss here what is an atomic spectra and what are the important types of atomic spectra. To understand the concept of atomic structure, it is important first to understand what the emission line and absorption line spectra, right? To understand the concept of atomic structure clearly, it is important to first understood what is meant by the emission line spectrum and what is meant by absorption line spectrum, right? So the solids, liquids and the dense gases emit the electromagnetic radiations at all temperatures. So here what happens? Solids, liquids and dense gases emits the electromagnetic radiations at all temperatures due to the oscillations of and interactions of their atoms and molecules. So these radiations have continuous band of many wavelength of different intensities. So that is what the continuous spectrum here. So when you get the continuous spectra, so it consists of what? A continuous band of many wavelengths of different intensities. So first figure you can see here the continuous spectrum. In that case we are getting here what? The continuous band of colors of many wavelength, and they are having the different intensities, right? But for less dense gases, what happens? On excitation they emit the discrete wavelengths, right? The what we call it as the rarefied or less dense gases, on excitation they emit the discrete means what here? The separate or specific wavelength, which appear to be what? A series of bright lines, right? So depending upon what the emission and absorption, we have the again two types of spectra here. One is line emission spectrum and the line absorption spectrum. So each element is having a specific characteristic of spectrum of radiation emitted by it. So every element shows a specific spectrum of radiation, right? That is what we call it here, what the spectra. Now let us study here what is meant by absorption spectrum, that is what a line absorption spectrum and line emission spectrum, right? So you know all what is meant by continuous spectrum. In case of continuous spectrum, there is a unbroken band of colors from a source sending out all visible wavelengths. So we have all the visible wavelengths here. There is a no breaking point in the band, so all the colors are visible here. There is in the form of continuous band, so that is called as what, the continuous spectrum. So when the ordinary white light is dispersed by a prism, you get the continuous spectrum. So what is a continuous spectrum? You can get it from the prism when a white light is passed through a prism. So that is what the continuous spectrum. But in this topic we are going to discuss about the line emission spectrum of hydrogen atom and also about the absorption spectrum. So I have shown here the two diagrams. What is meant by emission spectrum? What we call it as the line emission spectrum. It is the discrete lines, separate and specific lines we are getting here in emission as well as the absorption. And the second one, we have the absorption spectrum here, line absorption and line emission spectrum here. Now in detail, let us discuss here about what is line emission spectrum and line absorption spectrum. So here when an electric current is passed through an atomic gas or a vapor, now the atom is goes to excited state at low pressure. When it goes to excited state, after a short interval of time, it comes to ground state by emitting the radiations, right? By emitting the electromagnetic radiations, has a spectrum, right? The emitted radiation has a spectrum and which contains a specific wavelength, right? The emitted radiations is having the specific wavelength, and a spectrum of this kind is called as what, the line emission spectrum, and which consists of what, the bright lines on dark bands. So you can observe here the emission spectrum here, which consists of what, the bright lines on dark band. So here on a dark background we have the bright lines, right? Now how these bright lines are emitted, this is called as the line emission spectrum. When an electric current is passed through a atomic gas or vapor, that atom goes to excited state. After a short interval of time, it comes to ground state by emitting the electromagnetic radiation. So that is having the specific wavelength. It emits the radiations having the specific wavelength, and this is called as what, the line emission spectrum, right? So line emission spectrum, which consists of what, a series of lines of various wavelength. It consists of what, series of lines of various wavelengths. So in this case you can see here the red, green, right, blue, violet, in this way, right? In this way you will get a series of lines of various wavelengths emitted by an atomic gas by passing an electric current through it. That is called as the line emission spectrum, and this spectrum produced by the radiation emitted by an excited element is known as the characteristic spectrum of the element. For example, I will tell you two examples here. The spectrum of mercury vapor you can see here. So it emits the spectrum of mercury vapors emit the has a strong blue, and it is having the strong green line we get, right? This is the emission spectrum of what, the mercury, right? It is the emission spectrum of what, the mercury, which consists of a strong blue and strong green. So blue is having the wavelength of 436 nanometer, and the green is having the wavelength of 546 nanometer, right? So each element is having, which emits the radiation, right, which emits the radiation due to excitation, and which is having the particular characteristic spectrum, right? This is the spectrum of mercury vapor, which is having the strong green and blue lines, which emits when it comes to what, excited state to ground state by emitting the radiation. And this is the spectrum of sodium vapor. right? This is the line emission spectrum of sodium vapor, which consists of what? Which consists of what? Two strong lines we get here, two yellow lines we get here. One is having the strong line, which is strong yellow line, which is having the wavelength of 590 nanometer, and another one is having the lighter yellow line, dim yellow line, which is having the wavelength of 596 nanometer. So this is the characteristic spectrum of what? This is the characteristic spectrum of what? The sodium vapor. So what we can conclude from the line emission spectrum is what? The line emission spectrum of the, it is it is important for the what? The study of line emission spectrum, which gives an important, which serves as a what? A type of fingerprint for the identification of the gas. So which acts like a what? Fingerprint, right? So you get the two yellow lines, means we can identify it is what? It is a sodium gas. So in this way it acts as a what? The it acts as a what? Fingerprint for the identification of the gas. That is what the line emission spectrum. Now the next point here, what? The line absorption spectrum. What is the line absorption spectrum? The line absorption spectrum means when a white light is passed through a gas or wafer, and then the transmitted light is observed through the spectrometer, then what happens? Some it shows what? Some dark lines are observed there. So you can see in this figure absorption spectrum. So you are observing some dark lines, right? We are observing some dark lines on the bright background, right? So this type of spectrum is known as what? The line absorption spectrum. So in the, these dark lines are corresponding to what? Those present in the, those wavelengths which are found in the line emission spectrum, right? Those are absent in the what? The line absorption spectrum. So whatever the dark line you are observing in this case, these are the wavelengths corresponding to the what? Which are present in the emission spectrum, line emission spectrum. So those are absorbed in this case, so it shows dark in that space. So this type of spectrum is called as what? The line absorption spectrum. Now in this topic we are going to discuss more about what? The line emission spectrum of hydrogen atom. So this is the spectrum shown here is what? It is the line emission and line absorption spectrum of hydrogen atom. Now we are going to discuss in detail about this only, right? And one more important point here, we need to inform about you what? It is the electromagnetic spectrum. You should also know here at this point what is meant by the electromagnetic spectrum, right? So the electromagnetic spectrum means what? The whole range of frequencies and wavelength of the electromagnetic waves are arranged in increasing and decreasing order of the wavelength or frequency. That is called as what? The electromagnetic spectrum, right? The range of frequencies and wavelength of electromagnetic waves are arranged in increasing or decreasing order. That is called as what? The electromagnetic spectrum, right? So the electromagnetic wave uh, has a particular range of frequency and wavelength. Now in this figure you can refer here, we have the electromagnetic waves, radio waves, microwaves, uh, infrared, right? Next we have the visible light here, which is having the wavelength range from 400 nanometer to around 700 nanometer. Then we have the UV rays and X rays and gamma rays. So it is an electromagnetic spectrum. So only the visible light is having the wavelength range is from 400 to 400 nanometer to 700 nanometer, around round up we have told here. But we have in this electromagnetic spectrum, we have the range of all the electromagnetic wave with their frequencies, with the increasing order of frequencies or decreasing order of wavelength you can represent here, right? So in this, the gamma rays is having the shortest wavelength, right? As you move from this side to this side, the wavelength increases here, right? Gamma rays is having the shortest wavelength and radio waves is having the longest wavelength, right? And as you move from this side to this side, the uh, frequency goes on increases here, right? In this way frequency increases, in this way wavelength increases. So now this is what the electromagnetic spectrum you need to remember here. Now we are going to discuss the next point about the spectral series of hydrogen atom. Now we have to identify here the electromagnetic radiations emitted by these hydrogen atom, which are belongs to which series of this electromagnetic spectrum. That also we have to study here, right? Each element is having the specific characteristic of spectrum, and that belongs to which region of the electromagnetic spectrum also we need to study here. So that I have introduced here what the electromagnetic spectrum concept also, right? Now let us study here the spectral series of hydrogen atom, right? What is a spectral series of hydrogen atom? The spectral series of hydrogen atom, which includes what here? The line emission spectrum of hydrogen. That means what? Which includes a series of regions of spectrum, which are shown in the figure here. So we have the five series of spectrums or the regions in the line emission spectrum of hydrogen atom, as we have shown here, depending upon the transition of the electrons from the higher energy state to ground state or other states, right? Now we have the five series here: Lyman series, Balmer, Bastion, bracket, and P-Fun. These are the five series of spectral series of hydrogen atom. So we have shown here the energy level diagram of hydrogen atom with the principal quantum numbers n is equal to 1, 2, 3, and so on up to infinity, and the energy of each orbit, each energy level, E1, E2, E3, and so on. Alright. So when you get the Lyman series of spectral series in case of hydrogen atom, so in case of Lyman series, when there is a transition takes place from higher energy state to n is equal to 1 state, from what here? The higher energy state to what here? The n is equal to 1 state transition takes place. That means what? Electron comes to the n is equal to 1 state from the higher energy state. Then we get the Lyman series, and each line is having the specific wavelength. Then come to the Balmer series. Balmer series means what here? When you get the spectral series, that is the Balmer series. If there is a transition takes place from electron from higher energy state to it comes to the n is equal to 2 state, then you will get the Balmer series. Then each line is having the specific wavelength. Then similarly, Bastion series, in this case the electron comes to what? Higher energy state to n is equal to 3 state, right? N is equal to 4, 5, and so on to n is equal to 3, right? In case of bracket, what happens? There is a transition takes place from higher energy state to n is equal to 4 state, right? So electron comes to n is equal to 4 state from n is equal to 5, 6, 7, and so on, and from infinity also, right? Now again from the last series, that is what the P-Pun series. Here the transition takes place from what? Higher energy state to n is equal to 5 state. That is the electron comes to what? N is equal to 5 state from the higher energy state. So in this way, what is the during the transition, the electromagnetic radiations are emitted, which is having the specific wavelength, and that we call it as what? The spectrum, which is having what we call it as what? The spectrum. So each transition is having the specific wavelength and specific frequency, right? So now to calculate the wavelength or the frequency of the emitted line during the transition of this electron from the higher energy state to what? The different state, as we have classified the five series, right? Now we need to calculate the wavelength of the emitted lines. So for the calculation, we are using the Balmer empirical formula. We are going to derive here the expression for the wavelength of the emitted line, or the wave number equation we are going to derive here. So in the next class, we will derive the expression for the wavelength of the origin of spectral line of hydrogen atom. So how we are going to calculate the wavelength of these emitted lines, right? That we are going to derive the expression, that we will derive it in the next class, right? And once again we will discuss with that formula about this spectral series of the hydrogen atom. So you all need to remember about the today's class is about what is the spectral series of hydrogen atom and its five series, right? And what is an electromagnetic spectrum, the different reasons of different reasons we have here with their specific frequency and specific wavelength. For example, radio waves, micro, infrared, visible, UV, X-ray and gamma rays. These are arranged with increasing order of frequency and decreasing order of wavelength. In this way you can note down here. Now again, what is meant by line emission spectrum and line absorption spectrum, you need to remember here, right, about the atomic spectra and energy level diagram of the hydrogen atom, right. Energy levels are represented in terms of electron volt with the and you should note here what is the definition of ionization energy and what is excitation energy, right. And also these expressions already you know it, right, how we have done the calculation from joule to electron volt. So you all need to remember this about the today's class. So in the next video class we will continue about what the expression for the wavelength of the origin of spectral lines, or the expression for the wave number of the emitted radiation in spectral series of hydrogen atom. Okay, thank you students.